All right, 8 o'clock. Good morning. Well, good morning. It's been a long day. Good evening, everyone. How you people are doing? Good evening. Yeah, and Niha is here, so our TA. So welcome. All right, so let's get started. Go ahead. Questions. Someone is just starting on homework 7. Well, it's not too late, especially if you have late days. So and you can ask people who already submitted homework 7 how long it took them. So hopefully just a few hours. All right, come on, people, go ahead with your questions. Because otherwise, I'd love to stay in the call and chat about whatever. I'm a chatty type. Can you explain direct map to cache again? I'm not clearly understanding the tag. Uh, sure. So that would be a good starting point. So let's actually do the simulation. I think that's the easiest way to get it done. So let me. I will start sharing in a minute. So I'm just refreshing the browser page, and I will start sharing. All right. So we want to do direct map to cache, and let me just grab the parameters so that. All right. So 432. Well, we can do anything we want. So what size of cache do you want? Reasonably small, but all right. 8 it is. How large is our memory? 32. Okay, so that immediately allows you to answer the question: how many memory addresses you're gonna have competing for every line of cache, right? So it's 32 divided by 8, so 4 if I do my math correctly. So we're gonna have 4 memory locations per each cache line or cache block or cache entry, however you want to call it. All right, so submit, and here we are with our 8 cache entries. And up here we have our 1F, so is their last address, so it's 20 hexadecimal, so 20 times 16, so 2 times 16 is 32. That's how large our memory is. And then we need to do just issue instructions that reference memory. Okay, so here we have load and store. Those are the only 2 instructions that reference memory. Excuse me, and see how those instructions are going to be executed. So the initial state, we have valid bit 0 for all cache entries, which means we haven't used our cache. It's essentially empty. Of course, we have some data in here, and it's shown as zeros, but it can be anything. And we have some data in the tag fields, so it's also so we have, here it's shown as a dash, but in reality, we're going to have some, zeros and ones here, right? We only have zeros and ones. We don't have an actual dash here. So valid flag is what allows us to tell whether this cache entry is used or not. And now comes the analysis of our instruction breakdown. So we have an offset of 0 bits, and as I mentioned in the lecture today, so this simulator assumes that memory is word addressed. So in any examples that will follow the convention from the textbook or Zybooks, we are going to have at least 2 bits to address the byte in the word, because we would assume that the memory is byte addressed. So here we assume that the memory is word addressed. So if we did go for some non-zero offset bits, it would mean that we have more than one word per block. So we can, we can do that if you want, or we can stay at 0 offset bits. It's up to you. Do you want more than one word? So offset bits is all right. So let's go. Let's see what changes if we need to do reset and then 1. Right, 1. Okay. So and submit. So we have, oops, and it reset my other parameters. And I think I had 8 and 32. All right, 8, 32, and 1. Okay, so you see how things have changed as compared to our previous example, because now we have only 4 entries in our cache, because we have this data now is not 1 word, but 2 words, because we ordered offset bits of 1, which means that our block size is 2 words. And that means that if our cache size is 8 words, then we're going to have just 4 entries, right? Which we see. Okay, so memory size of 32, that's their maximum memory. That basically determines the number of address bits that we need to address this memory. And this number is 5, right? To address 32 cells in memory, we need 5 bits. So given that 1 bit is the offset, so it is the number of, so it helps us address the word within this 2-word block. And then index is 2 bits, because we have 4 elements, 4 entries in our cache, and 4 is determined as 8 divided by 2, and 2 is determined by this bit, so it's 2 to the first power, and a 5 is determined from this 32, right? So it's 2 to the 5th and is 32, therefore 5 is the total number of bits in my address. Okay, so we have 1 offset bit, 2 index bits, and what is left is tag. And what is left in this case is 2 bits. So offset bits is the word for this simulator, yes. And if you are following the convention from Zybooks, then you would add to it 2, because we also need 2 bits to address the byte within the word. Okay, so if we were doing this example based on the assumption that our memory is byte addressed, then we would have not 1 bit of offset, but 3 bits of offset, right? Because we would be addressing bytes within 2 words. So 2 words is 16 bytes. So we would need 2 words is 8 bytes. All right. Getting confused myself. So 1 word is 4 bytes. 2 words is 8 bytes, and to address a byte within 8 bytes, we need 3 bits. Okay. So now all the ends, tied together. So 3 bits, 8 bytes that we have within this block of 2 words. All right, and basically their calculation is given here. All right, so you can verify. So basically everything I said right now in much shorter form is given here. So offset is 1 bit, index bit is log base 2 of a divided by 2, and instruction length, that is the number of bits for the address is 5 bits, and so the rest, tag is self-explanatory. It's just whatever is left from the instruction breakdown. So load or store, this doesn't really matter that much to us for now until we are concerned about their write policies, right? And how their dirty bit operates. So we can get started with just reading with load instruction, and then if you want, we can also play with what happens when we have store instructions when we are writing to the cache. If it's a bit instead of word, then offset gets increased by 2, but that doesn't affect the tag, correct? Well, if you change nothing else, but you increase the size of the block, then it does affect the tag because there are fewer. There are fewer bits left for the tag. So imagine if you want to maintain the same number of cache entries, so your index would be the same, right? So if you increase this offset, invariably you're going to have fewer bits for tag. If, however, as in this simulator, which one of their input parameters is the total cache size, so we saw how when we adjusted the number of bits in the offset, the organization of the cache changed. So we now have 4 entries instead of 8 entries. So the number of index bits decreased by 1 so that the number of bits in the tag stays the same. Okay, but if one of our parameters, input parameters, like configuration parameters of this cache was not the total cache size in the number of words, but their number of entries, then if we increase the offset, index stays the same. Obviously, tag has to be fewer bits. I hope Kuzmin Easy doesn't use a save instruction. Huh, that's a good idea. I haven't thought of it, so I'm glad you mentioned it. I'm just kidding, but you might get something related to write instructions. Don't be afraid. That's you can ask questions. No, I know for the most part I'm kidding, but I'm not kidding. You might get store instructions. So just be prepared. Don't be afraid of them, and you're gonna be just fine. All right. So finally, let's do something. And whatever address we want from 0 to 31, right? Because our memory size is 32. So I don't know. Let's do 2. Submit, and so this is our address, right? So it is 2, as you can see, 0, 0, 0, 1, 0, and which means that their index is going to be 0, 1. So it's going to be this entry. All right, and then we look at the valid bit. Valid bit is 0, so we know it's a miss, and we have to bring their block into the cache. And next, our hardware still has to do the whole thing, analyze their valid and tag, because they are all input to this AND gate. Of course, we know since one of the inputs is 0, the result is going to be 0 or false. So it's going to be a miss. And then we are bringing in their data. Note that we are bringing 2 words, and that's why it says here word 0 and 1, because our block is 2 words. Okay, so we only requested word at address 2, but we are bringing their block of 2 words, so words at addresses 2 and 3. Okay, so and now let's finish this instruction. And of course, it's a miss. So can someone tell me what would be their address that I need to reference in my next load instruction so that it is not 2, which we have done as our first instruction, but which would guarantee that we have a hit given the current state of our cache? Exactly, it's 3. So we never requested 3 before, so why do we expect that it's going to be a hit? Well, because when we requested 2 and we got a miss, we brought in both 2 and 3. So now 3 is in the cache, right? So 3 is this word 1 from this block 1. So let's make sure that it is indeed the case. So note load 3 maps to the same block, right? Block 0, 1, and now, of course, the valid bit was set to 1 when we brought that double word from memory in there when we were processing the previous instruction. And tag is 0, 0, and tag here is 0, 0. So that shows why we use a tag and why we need a tag, because there are several different addresses that map to this same cache block. Okay, so it's not just 2 words that are part of the same block. For the cache, that block is indivisible, right? So whether we are requesting 2 or 3, the cache would treat them as parts of the same double word block. So, and there is no competition between word 2 and 3, right? Because they are part of the same block. They would either be in our cache, both 2 and 3 together, or none of them is going to be in their cache, right? Because they are part of the same double word. So the competition that I'm talking about is the competition between other double words. Okay, so and we will see how that works. So for now, we know that it's the right block because our tags actually match. And my next question to you would be, can you give me a memory address that would correspond to a different block, that double word block, but that would map to the same cache entry with cache index 1? Anyone? 0, 0? Okay, let's imagine 0, 0. What would be their index of address 0? So imagine for the 0, right, it would be 5 zeros. So it would actually map to index 0 here, not index 1. So 2, but 2 is something that we just had, right? So 2 and 3, yes, those two addresses, they are part of this block that would have 0, 1 here and 0, 0 here. That's true, but I'm asking for something different. 100, can we have 100 here? No, because we only have memory that has 32 elements. If we had 100, we would have more bits to address 100 cells in our memory. And we only have 5 bits because we only have 32. Oh, 100 in binary. Well, 100 is not a full address. All right, full address is 5 bits. So did you mean 00100? Okay, that works. Okay, yeah. But what would be, so I'm looking at the chat, so hopefully you can see their most recent message in the chat. So what would be their index for this address 00100? What would be the cache index? It would be not 1. Well, can you give it to me in binary since we started binary? So let's keep doing the binary then. It would be 1 0 exactly. So if you look at 0 0 1 0 0, that would be counting from the right, the second and the third bits. So it would be index 1 0. So it's not going to be the same index, right? It's going to be index 1 0, which would be this in the this entry in the block. And I'm asking for another address that would be in the same block as our addresses 2 and 3. So 0 1 0 1 1. Okay, that I agree. Okay, you see, if you look at the second and third bits from the right, they would be 0 1. So they map to the same block, but it would be a different tag. A tag would be 0 1, whereas here tag is 0 0. Okay, so and 0 1 0 1 1, it would be 0 1 2 3. So 8 and 3, it would be 11 if I'm not mistaken. So we can make a mental note and then try 11 as our next instruction. Okay, 11 decimal, and I think here it's in hexadecimal, so we need to do it B. Okay, so just make a mental note, do load B as our next instruction, and see what happens, right? Because it would map to the same block, and that block is already used by our double word that includes addresses 2 and 3. All right, so for now we are continuing with load 3. And we see that valid bit is 1, tag matches because it's 0 and 0, and we have a hit. So excellent, right? We were able to find the data from memory for the address that we have never encountered before. So that is a hit, as we can see, and it's good. And that is one of the biggest benefits of having more than one word in a block, of having larger blocks, because you have miss at some point, and then as a response to this miss, you bring in the whole block, which can be multiple words. So if you are expecting that your memory access pattern exhibits a lot of spatial locality, meaning that, oh, if I access this address, then it's very likely that very soon I'm going to need the immediately following address and then the immediately following and so forth. And so if you have a larger block, then on subsequent accesses, you will be getting hits, you will be hitting on those addresses, despite the fact that you have never actually accessed them before. So when we say, I accessed it before, and so I hope I would access it in the future, this is temporal locality, right? Because it refers to the time, future, and the past. When we talk about spatial locality, it's about, well, I accessed this location, and then if I access the location that is nearby or like immediately adjacent, then I would like to, preferably have, a higher probability of a hit. So that's hoping, that's exploiting for the spatial locality. All right, so this cycle has been completed, and so next we were going to try B and submit. And you see that indeed this is the breakdown. We are still pointing to the same cache entry at index 1, but the tag bit is different. It's 0 1, and therefore we already see that, yeah, valid bit is 1, but there is a mismatch between the tags 0 0 here and 0 1 here, so it's going to be a miss. And it makes sense, right? Because it's not this B address is not part of the word of the double word that we have cached. That one had addresses 2 and 3 from main memory. So this is B. This is a completely different address, and therefore it is going to be a miss. All right, so valid bit, and then comparing tags, and oops, that's a miss. And we're gonna bring double word that contains B and some other word. Can someone tell me what would be the address of the other word that we will bring in to our cache, replacing, of course, this block that contained 2 and 3, the values from addresses 2 and 3. So what would be that block that we are about to bring into our cache? So it's going to be B, and then is it going to be the next block, so C, or the previous block, A? All right, exactly. So it's going to be, all right. So we have two options, right? So someone is saying we're going to bring in 0, 1, 0, 1, 0, which would be 10, which would be A, and someone says C. All right. So can you support your point of view? Why A or why C? 10 is even, and 1 and 13 isn't. Okay. Yeah. Change of the answer. And really, it's very easy to see because there, if we are talking about different words within the same double word block, then the only difference would be in this bit, right? For our case, when we only have 2 words in a block, then the only thing that would change would be this. And this one is for our case of B. Okay, so when the only other option that would correspond to the same block would be when we have when we have 0 here instead of 1 as their least significant bit. So it would be, as Miles pointed out, 0, 1, 0, 1, 0. So if you just write it in binary, right, you can just keep your index and tag intact, and then go through all possible combinations of your offset bits, right? It's easy when it's 1 bit. It's going to be a little bit more work when if you have an even larger block with more than 2 words per block. And then all the combinations of your offset would correspond to the same block, and that's how you do it. So if we attempt to do, all right, so if we, yeah, let's finish this one. So we have to replace the old value, right? It has to go away, and now we brought that address B in along with address A, as we already figured out. So of course it was a miss. But now if we attempt to load A, okay, so that should be from the same block. And it doesn't matter that when we brought in this block, we actually we're trying to reference the second word in this double word block. It doesn't matter. If we are trying to access any word within the block and it is not, that block is not in the cache, then we're going to bring the entire block. So let's submit A, and we see that yes, indeed, the only difference from B is that it's 0 here, and next, and we already see that tags match 0, 1, 0, 1, and it's a hit, and we are all good. We are back to the miss rate of just 50%. All right. So does that make sense? Does that clarify why we need tag and how the sizes of all those components, BOB, index, and tag, are computed? So there are 32 memory blocks, yes, in this example. If you think about your MIPS processor, that would be hold on. Let me take it back. Let me take it back. There are 32 memory addresses. Each is 1 word. So when you say 32 memory blocks, well, we say block when we mostly talk about the cache, okay? Because cache might have, several words per block. When we are talking about memory, it just however your memory is addressed, that would be your block. And in this case, our memory is word addressed, and the majority of cases when we have examples following the convention from our textbook, memory is going to be byte addressed. So you're not really talking about blocks in the context of memory. Okay, I just wanted, to make it clear about the terminology. So yes, in this example, memory is 32 words, and this cache can hold only 8 words, even though there are 32 addresses. Yes, because if you're because we have basically a ratio of 1 to 4, so our cache is 4 times smaller than memory. Okay, if you have your cache as large as your memory, then you don't need cache, right? You just well, you don't need your main memory, right? Because your entire cache would contain all the values that you want. But typically, main memory is very large, like gigabytes, and cache would be much smaller. Typically, depending on how many levels of cache you have, and depending on the organization, it might be from a few kilobytes or even less to a few megabytes at most. And in like desktop processors, you would typically have more levels of cache, and cache would be cache size would be larger, like order of megabytes, probably a few megabytes, because in a desktop processor, I know you're paying so much for desktop processors, or consumers pay so much for desktop processors, that, of course, we can afford a lot more cache than if it's a processor for embedded applications. Like think about your dishwasher or something, something similar. Then, of course, the entire processor should probably cost like couple dollars. So obviously you cannot afford having many megabytes of cache in those processors. All right, where do we go from here? So I think I hopefully answered the original question about the tag and all that. So where do we want to take it from here? Oh, dirty bits. All right, yeah, that's an exciting thing. All right, so dirty bits only used when we have writes, when we perform writing into our memory. You see, we had dirty bits from the very beginning, but they are all zeros, and because we never wrote. So dirty bits have to do with this write policy, and and if we are doing write through, we don't really need dirty bits, because recall, with write through, every time we write a value to memory, we update it both in cache and in main memory. So our cache and main memory are guaranteed to be always in sync, so we don't need any dirty bits. And yeah, someone is asking about the scope of their test. So yes, it's pipelining and cache. That's pretty much it. So up to everything that we covered today. So obviously, that dependable memory part that we didn't get to is not going to be on the test, and I can tell you exactly what it is called and where we stopped. So not here. We didn't get so far. Yes, so we stopped here at this slide, and we didn't start this dependable memory hierarchy. Okay, so and their numbering of slides might change slightly, because yours might not have like some couple slides with their answers to pop quizzes, right? But you can just go by the name of the slide. Okay, so that's where we stop, and it basically ends their cache topic. Okay, so which virtual machines, and then virtual memory. So that's going to be on our next test, not the one that is tomorrow, but the one after that. So hopefully you don't think that computer organization is going to end. All right, it's just going to continue and chase you and be your be in your night dreams. Hopefully not nightmares. It'll show up on the Fox panel. That's a good one. Yeah, I kind of like it. All right, back to business. Where were we? All right, we we were here, and so let's try writing something. So right through, we don't need dirty bits. Right back, we when we write, we would only update our cache and not the main memory, just to save time. All right, so we currently have this block that at index 1 that contains addresses A and B cached. So let's store into A or B, doesn't matter, right? Let's store into A. Okay, so we submit this instruction. Can someone predict what is going to happen? Are we going to have a hit or a miss? Yeah, it's going to be a hit for sure. So let's verify that our thinking is correct. So we converted the instruction to binary, and then you see, because it's a store instruction, we it immediately tells us, yes, we're going to be following the write back policy. So cache will be updated with the dirty bit. Okay, and so we have this, and so requested address is found in cache table. All right, so effectively it's a hit, and we are updating. So we are writing the new value for address A, but it's only going to stay in cache here inside this double word, and to indicate that it has not been yet written to main memory, this dirty bit is set. All right, and that's it. This ends it. So now what happens if we have any operation, and let's do a load again. So when will it be converted to the main memory? Yeah, I wouldn't call it conversion, right? But it has to be written to main memory at some point. So how long can we keep this, this block of cache out of sync with the main memory? So obviously, until we are forced to evict this block from the cache. So when until we have to replace, until the next instruction that stores A. Okay, we can try that, store A. Does everyone agree that it is going to cause a write to the main memory? Any thoughts? No. Okay, exactly. Because when we are writing to either A or B, we are writing to the same, to the same block of values, right, to the same double word that we have stored here. And this block is already marked as dirty. So, you can only get so, dirty so much, right? You cannot get any dirtier. And the same applies to this block of data in the cache, right? Dirty means that some data here, and we have two words here, so one of those words or both words need to be written into the main memory. Okay, but if we have another store operation, we can just update it in the cache. We don't have to write to main memory, right? Because this block is already dirty, and yeah, it will not get any dirtier, but we are not going to lose their new value, right? It's just going to replace the previous value that we stored, the previous value that we wrote, and that is currently in our cache. So, and I think I submitted, so we can just do next, write back policy, and we have this hit on the cache, requested address is found, and so cache is updated and dirty bit is set to 1, and you see that we had 2 hits. So only if there's an overflow of the cache. Well, overflow is not really the term that we apply to cache, right? Because like, what do we mean by overflow? So if we attempt to, let's say, load, and you will hopefully tell me which address I need to load from to cause this block to be evicted, to be replaced by the new block. So when we have this other address that causes this block to be evicted, then if we just erase this block, if we replace this block with a new one, then we're going to lose all our values that we have written into cache, but not main memory. So that's the ultimate point where we have to update our main memory. Otherwise, our store instructions are going to be lost, right? The result of those store instructions is going to be lost. And that's exactly what happens. We only store to main memory when we replace the block that contains their changes, and their presence of changes is exactly signaled by their dirty bit being 1. Okay, so technically, like, it's not an overflow, right? Because we have 3 entries in our cache which are not used at all, right? But it's a direct map cache, so we have this enormous competition for for this single block, right? So we actually have 4 entries so in our cache. So we are going to have 4 double word blocks competing for this single entry in the cache. All right, so which address do I need to load from? And obviously there are 2 options, right? Because we can load from any of their words within their double word. So which address, give me one of these 2 addresses that we need to load from to cause this block to be replaced. All right, 00010. Okay, so their index would be 0, 1, so it would be the same block, I agree. And then their tag, their leftmost 2 bits would be 0, 0, so it would be indeed a different block. So I agree, and yeah, 0, 0, 0, 1, 0, oh, it's going to be 2 again. Well, we tried it, but of course it's going to work, all right? So I was just hoping you were a little bit more creative and picked one of their blocks that we haven't encountered. But it's okay, it works. So we submit, and so we see that yes, this instruction points to this block in cache, and we look at the valid bit. It is 1, and then we following is their analysis diagram. So we look at the tag, and tag is 0, 0, tag is 0, 1. So mismatch. So it's going to be a miss, and therefore we are going to replace this block 5 that we currently have stored. And since dirty bit is 1, right, our memory will be updated. So before kicking out this block, we would just write this whole block, right? We don't know which of the words within the block were changed, or both of them, right? There's only one dirty bit per block. So the only safe option is to write both words from this block to our memory, right? And so it means that we will write both address A and address B in our main memory, and then we kick out this block 5, right? This highlighting shows that it has been just updated, and then we bring in block 1 that contains addresses 2 and 3, right? And you see how dirty bit went to 0, right? Because the block that we currently have, it is clean, it is not dirty, and therefore we are back, okay? And note that dirty bit, how it is, different in many ways from the valid bit, right? So dirty bit can go, 0 to 1 and then back to 0 many times. Valid bit can only switch from 0 to 1. We will never see a valid bit going from 1 to 0, right? Because since we've used this block at least once, then this block is always going to contain some value, right? We may replace it with another block, but then it would still be a valid block, right? There's no sense of just removing this block from cache and not putting anything else in the cache. Does it remember that there? All right, so let me read it in order. If memory update is slower than cache update, couldn't you start the memory update when there are cache updates, and then after enough cycles, the memory will be up to date also? Yes, this is typically what is done, but it's not as trivial as you might think. Because what if the memory is so slow that by the before it is done writing the previous update, you have another block that you need to write, okay? Because we only have single memory, and well, we might have different memories, but then typically each memory would have its own cache, like instruction memory, instruction cache, data memory, data cache, right? So our cache works with a single memory, and that memory only supports reading and writing from one address at a time. So it's not like your register file, which is called register file because it supports reading and potentially even writing to from multiple addresses at the same time. Traditional memory, it's just one address at a time. So what if your main memory is still writing the previous update and it needs to to write another update? It may be even from a different block, it doesn't matter. Okay, so that creates a problem, and then as we mentioned in one of the slides, a solution to that problem might be a buffer. So you can increase the depth of the buffer, but then of course the problem becomes how deep that buffer needs to be. So you need to analyze the to actually compute with with specific numbers how fast your main memory writes to compute the optimal size of the buffer. Okay, so hopefully I answered that question. Moving on to the next one. Does it remember that the dirty bit of block 5 is still 1, or does that go away? No. Once block 5 leaves the cache, then we don't need to keep the dirty bit at 0, at 1, because block 5 is no longer in our cache at all, so it's gone. And that's why this dirty bit now, which is 0, it belongs to block 1. It says that block 1 is clean. So block 5, as far as cache is concerned, it's history. Also, if valid bit can never go from 1 to 0, what does clearing your cache do? I don't know. Where did you read clearing your cache? I mean, in other contexts, it might make sense, like clear your browser cache, right? Where you just where you just remove all all data, all pages that your browser saves, hoping that you might need it. But in this concept of the cache, right? Cache referring to the interaction of the processor and memory. You don't clear the cache, right? The only time when valid bits are set to 0, they are all set to 0, all valid bits for all cache entries, and that happens as part of their power up procedure, right? So when you turn on the power, there is a special reset signal that is generated by, usually hardware that then, is usually inverse, so it's active low, and when that active low reset signal is routed to all their essential components of the circuit, and then it sets all those circuits to a known initial state. And for the cache, that would be guaranteeing that it sets all valid bits to zeros. Yeah, so when you turn your computer off, so you cannot even say what the state of your memory is, right? Because if it's not a non-volatile memory, then when the power is off, its contents is lost, or lost pretty quickly. So I'm sure you've heard older stories, which are true, that if the computer has been powered down very recently, you can kind of spray it with liquid nitrogen or something to stop like older you know electrons from moving, and then you might still be able to recover the contents of their memory, even though the power has been removed. But yeah, it's a technology for some three-letter agency, not for us common humans. All right, so that's their write back, and that's their dirty bit. So what if we want to store into memory location that is not in their cache? So can someone give me an address that would make use of this index number 2? All right, 00101. Yes, so 10 would be the block number, right? So their second and third bits from the right. I don't think 10000 would do it. All right. So I'm going to go with 00101 from G, and so it would be 012. So it's going to be 5, right? So I'm storing 5, and note that I'm storing without previously loading. Is that weird? Not at all, right? So how is our cache going to respond to this? Well, first off, all right, we break it down. So we figure out that it maps to this index 2. So we have write back policy. So the cache will be updated and the dirty bit will be set to 1. Okay, so because it's a miss. All right, so and we see that it is indeed happening. However, it is happening like that because we are using write on allocate policy. So it means that even so when we have a store operation, a store instruction referring to a missing address, to an address which is not currently in the cache, we would bring that value in. So we would first go to main memory, read that entire block of 2 words, put it in the cache, then update one of those words, right, the one that is referenced in our instruction, and then set the dirty bit to 1. Oh, okay, hold on. No, I take it back. So we will. Let's do another one. I just want to verify before I say anything else to make sure that what I'm telling you is exactly the correct thing to say. So let's do 1 1. So it would be 7, for example. All right, we convert the instruction, write back policy, cache will be updated with dirty bit, and search is performed to determine whether the address is in cache. It is not. Requested address is not found in cache table. I agree. Cache does not contain requested tag. Data is loaded and content is updated based on the write on allocate policy, which means we bring that that value in. And yeah, I don't see the dirty bit being set. I believe this is wrong. So I believe the simulator is wrong because we should have this dirty bit set to 1. Okay, because we were writing to the memory, and obviously we brought in the value and we changed it in the cache. We didn't change it in the memory. Okay, so I believe that dirty bit should be set to 1 in those cases. Isn't dirty bit just for write back method? But we do write back. So see, we have write back. If we had write through, there would be no dirty bit. So we I can show you later. I just don't want to reset this configuration now. But if you switch it to write through, the dirty bit column is going to disappear. So that part is done correctly by the simulator. All right. So well, why don't we look at write around, right? So write around is actually pretty easy. So let me reset it. It's so 832. Well, I can just submit it. So let's do write around. Well, let's do write through just to see how that works. And I submit it. Is anything going to happen? Okay, I guess I need to reset and then submit. Okay, but it reset it. All right. Anyway, so we want to do write through 8, 32, and 1 and submit. And yeah, it actually didn't get rid of the dirty bit, but it shouldn't be used. So we can try store 2 and well, we can load 3 first just to bring it in, for example. So submit. Next. It's a miss. We bring 3 in, and then we are trying to store 3, and we submit, and it's a write-through policy, so memory and cache will be updated at the same time, and so it's a hit. But you see that memory block is updated. All right, maybe on there. It's going to show it now. No, okay. But memory has been updated. I know why it's not highlighting it. It should be updated. And you see that the dirty bit is not set to 1. So essentially, it's never used with the write through policy. And then the last thing that since we are playing with those switches anyway, so why don't we try write around, and we can switch this back to write back and 8, 32, and 1, and write around, submit. So the difference between write on allocate and write around is what is going to happen on a write miss or store miss. So let's say we are storing into address 3, and obviously it's a miss, but because it is write around, we are not going to bring it into the cache. We're just going to update it in memory. So now it is highlighting correctly. You see, so we just wrote directly into the main memory, and we didn't bring that value into cache. So that's the difference between write around and write on allocate. And write around can be very useful if you are, for example, initializing large areas of memory, right? Or you're trying to zero a big chunk of memory, right? Obviously, you don't want this to be in the cache, right? Because it's just going to be slower. So you're just going to, write directly to main memory, and that's it. Okay, so that's direct mapped cache. Anything else you think I'm missing? Any questions on this? Anything related to this? All right. So what do you want me to do next? Please go ahead with other questions. Cache misses. What about them? Could you please be more specific? Could you please give a quick recap? Sure. So quick recap would be a miss is a situation where you have a memory access instruction, whether it's load or store, that references address, and the value from that address in main memory is not resident in the cache. So then it means that we cannot retrieve the value from that memory address or write the value to that memory address if it's a store instruction, in our cache. So we have to, if it's a load instruction, we have to bring it in from main memory, put it in the cache for future use, and then satisfy the instruction from the cache, right? So once the value is brought from main memory and placed in our cache, then cache can serve that value up the hierarchy to the processor. If it's a store instruction, then it's going to be similar, except for now there is this effect of the write policy, write on allocate versus write around. If we have a write around, then cache is essentially bypassed, and when we store and the value is not in is not in cache, we just write to our main memory. So it's going to be a hit. It's going to be a miss, but we are not bringing the value into cache anyway. If it's write on allocate and we have if we are trying to store into the address that does not have the value from that memory address in the cache, then we first bring that value in. So it's going to be a miss. We bring that value in and we keep it in the cache. Is that making sense? Can we go over associative caches? Sure thing. So the problem, direct map caches are, very, very simple. I don't know if you agree, but they're simpler than other types of caches. Okay, and there's nothing wrong with them except for, as we have seen in the examples that we did earlier today, that we might have a competition for the same block that causes evictions, that causes data that is stored in that block in cache to be replaced with with their data from other memory addresses, while other entries in the cache are sitting there unused at all. Remember, I think we were playing with these two indices, with these two blocks, and we had some replacement happening, whereas our block at index 0 and our block at index 3 never had their valid bit changed to 1, right? So those are unused. And that seems a little kind of foolish, a little wasteful, because why would we want to evict to replace a value which we could have kept for maybe it's going to be needed in the future, while we could have placed that value that we need to find the room for in one of the other blocks. And that's the entire idea behind associative caches. So with our associative cache, oops, this is virtual memory. We didn't get there yet, right? So with associative caches, we say, all right, so we can designate a certain number of elements in the set. So we can break our cache not just into entries, right? So we would think about our cache not as a certain number of elements where several memory addresses compete for any given entry, but we organize entries into sets. And now memory addresses will be competing for entries in the set, not in just one entry. So if we have a two-way set associative, this two means the number of entries, and you see that the formatting that we get from this tool is exactly two sets. So we can try something. So let's do cache size 8 and 32, and we can go with 0 offset bits or not, it doesn't matter. And now the replacement policy is a thing, because previously we didn't have a choice which element to replace. There was only one option. So now with a set of size 2, if we have the entire set full, we have a choice of which of the two elements to replace. And so FIFO is not really even mentioned in your slides, but LRU and random are mentioned, and so all three. And there are other replacement policies, a little bit. Some of them are a little esoteric, but LRU and random are probably the most common. So let's go with LRU. LRU stands for least recently used, and it kind of makes a very intuitive sense, a lot more than random. And LRU, of course, is more expensive to implement, but the rationale is really straightforward. You replace if you need to evict someone, you evict your oldest tenant, right? So because you think, well, if they've been here long enough, and so maybe no one came to visit them, well, maybe no one will come to visit them in the future either, so I'm going to evict them. All right, so submit, and this configures our cache. So we have, oops, we have 4 sets. We have 4 sets and 2 elements per set. So now the index corresponds to sets, and we have index, which is 2 bits, and we have tag, which is 3 bits. So compared to a direct map cache, you see that the more associativity you have, the all other things being equal, the fewer sets you are going to have, and that means that the fewer indices you will need to to enumerate to address your sets, and the more bits you're going to need for the tag. So in the in the limit case, when we have a fully associative cache, there's just one set. And that means that with one set, we don't have a problem finding a set. So index bits is going to be 0. And that means that pretty much the entire address, apart from their offset, is going to be in tag. So you can imagine that's why when we are comparing entries, trying to find out if we have a hit or a miss, for fully associative sets, we would have to go through all elements in the cache, right? Because they all belong to the same set, and we have to basically search through the entire cache to see if we have a matching tag and valid bit. and that is very expensive. In the majority of cases, this is prohibitively expensive. There are still fully associative caches, but they are not that common because they are very expensive. All right, so now we with those 4 sets and 2 entries per set, note one extremely important thing. So a two-way set associative cache is not the same as the direct mapped cache with a block size of 2 words, which we played with before. Okay? So it may look like it's similar, but it is actually not. See how here we have data, which is in our previous example, direct map cache, we have data which is 2 words. Okay, so it's a double word, but it's still a single entry, which would have a common valid bit, a common tag, and a common dirty bit. So we are basically just increasing their size of the block, but we are not making more entries in our cache table. Of course, the total size of the cache would depend on on how large your data is, on how large of the block you have, but each entry would still have its own valid tag and dirty. Whereas with a two-way set associative, we have 2 entries in a set. So this is our set number 0, and it would have a valid tag, dirty, and data for the first entry, for the first element of the set, and valid tag, data, and dirty for the second element of the set. And of course, whether we have dirty bit or not will depend on the write back versus write through. But as we already figured out, this tool probably shows this column anyway. But in reality, if you have a write through cache, then you're not going to have a dirty bit. And I can give you an explanation why probably this tool does it this way, because you would probably never see a write through cache, right? Because it's extremely inefficient. So the majority of caches that you are likely to encounter would be either write back, or most common case is the cache is configurable, write back or write through. So it's like software configurable. So you can switch it to write through, temporarily if you think there is a task that would take advantage of the write through policy, but it has to be configurable, because if it's just stuck at write through, it's not a good general purpose cache. So yes, write policies can be dynamic. Yes. Okay. So and let's play with this cache. So we have let's try with load 3. So can you tell me what sets the write policy then, or should we know? Well, usually the user sets, or the program, or right. So usually it's software configurable inside the processor. Some very old processors, and I don't remember if Intel was doing this, but AMD, its early processors had it configurable in hardware. So there was like a jumper on the board that you could, on very early, or very old PCs, desktop machines with AMD processors, there was actually hardware, a jumper that you could, set if you wanted your processor to be write through. But then very soon they switched to making it configurable through BIOS setup. So this, this very basic configuration thing that you can invoke if you press, some magic key when your computer loads. It's usually like F1, F2, del, something like that, and it brings up this text mode configuration thing that lets you configure certain properties of your processor. So for processors that had this write policy configurable, write back versus write through, that was in that BIOS setup page. So that was configurable, but once you configure, you had to basically restart your computer. So it wasn't very convenient. All right. Load 3, right? That's what we are going to do. So this is the breakdown. This 1 1 or 3 now refers not to the entry, but it refers to the set, right? We only have 4 sets. See how we have 4 sets and 8 entries, despite the fact that we have 0 for our offset. All right, and so that's that, and obviously it's going to be a miss. But see how we check both entries in this set in parallel simultaneously, right? Of course, that requires more hardware. So we now need to have 2 comparators and 2 AND gates, and then an OR gate to check if we have a hit or a miss. And it's a miss, obviously, right? And here we are. And now we are bringing the value in, the value from address 3. Where does it go? Well, the first rule is it goes to an entry that has a valid bit of 0. And if both of them have valid bit of 0, then it's arbitrary, right? We might have it deterministic, or we might not. It really doesn't matter. Okay, so of course, this tool will always act deterministically, so it will just put this in the entry with a smaller number, right? If given the choice between 2 equal opportunities, it will prefer this entry, like the first entry, if you will. But it's not necessarily, it doesn't have to be that way. Nothing would change if we placed this value in the second entry. It would not change anything. All right, so now let's see. Obviously, if we now load 3 again, it's going to be a hit. But I wanted to um, to have uh, to have you tell me what would be an address that would map to the same set, and that would not be 3. Obviously, we already tried 3. So give me an address that would map. All right. So 001110. Okay, so the important thing here is that the second and the third bits from the right are 1 and 1. Okay, so these bits are 1 and 1. That's what determines which set we are in. Okay, so yeah, I'm good with. Oh, hold on. This is, yeah, this is a little bit misleading. This is 0 bit, so this thing is not here. So we need 2 least significant bits to be 1 and 1. So yeah, so yeah, it's 00111. Yeah, because we still have only 5 bits in our address. We still have memory size of 32. I know this 0 is really confusing. All right, so 00111. So which means the tag is going to be 001. So this is address 7. All right, so let's do 7. Happened. Oh, I didn't. All right, so yeah, now it finished, and the previous step, I didn't finish the previous step. All right, and 7. All right, so it is the same set as we can see, and it's still going to be a miss, right? So it's still a miss, despite the fact that this valid bit is 1, but the tag doesn't match. Okay, so it's going to be a miss, and we are bringing this new value from address 7 into the cache. Where do we put it? Do we replace our cached value from address 3? No, right? We have room here because this valid bit is 0, so we can we can bring it in. And here we are. All right. So that's the beauty of associative cache. All right. Associative caches. So because now we have both 3 and 7 in the cache. And yes, so this set is now full. So what can you give me another address which would not be 3 or 7, which would still map to the same set? 10011. Yep, sounds good. So it's going to be 4. So it's going to be 16 and 18 and 19. Did I do my math correctly? It's going to be, oh, it's 19. So it's going to be in hexadecimal. It's going to be 113. Okay, so we need to finish the previous step though. All right. So is it going to be 13 hexadecimal? Did I do that right? I think so. Yeah, it's 1 and 3. All right. We submit. All right. It maps to the correct set that we wanted for our example. And their tag bit is different than any of the tag bits that are saved here. I don't know why it is why it is showing just with with one value. Probably it switched for this simulator. It shows it in decimal, not in binary, right? Because it has to be three binary digits. But we shall see. Now we have 100, okay, for the tag. So obviously, despite the fact that both valid bits are 1, it's going to be a miss because there would be a mismatch on both tags. And here we are. It's a miss. And now we have this thing, right? So we have to read the value from main memory from address 13 hexadecimal. And that means that we have to, evict one of our existing blocks from this set. Do we evict 3 or 7? Remember, we have the least recently used. Okay, so which one was least recently used? 3 or 7? And you can look at the history here. If you don't remember, this is the list of previous instructions. 3 is the oldest. 3 is the one that was not accessed the longest, right? Because 7 was accessed in the previous instruction, and 3 was accessed 2 instructions ago. So 3 is the least recently used. So if this simulator is correct, it's going to evict 3 and put 13 here and update their tag correspondingly. So let's see if this indeed happens. Right, cache replace the old index. There is, dirty bit is 0. So, and you see that it is indeed what happened, right? We replaced this with block 13 and we are done. Okay. So does that demonstrate the advantage of associative caches? And so obviously, because we are, we have more freedom in where we place the values that we need to bring in. We have fewer replacements, and that means that we are going to have, on average, we are going to have fewer misses. But the price that we have to pay is the additional hardware, because now we need to compare tags for all their elements in the set. And yes, I was correct. So they just show tag as decimal in this view, probably because they couldn't otherwise fit it on the screen. So indeed, our tag is 100. So this is 4. So you see that everything is looking good. All right. more questions. Hopefully I answered the question about the associative cache. Looks better than good. All right, I like your optimism. Well, we still have like half an hour, which doesn't mean we have to stay. I mean, if everyone is tired and there are no more questions, we can just call it a day. Well, it's not going to be the end of my day. I still have to write their exam, but hopefully most of you can get some decent hours of sleep. Oh, you want to know more about caches? Well, coming from a mentor, that sounds a little provocative. So next thing you're going to be asking, Nana, is for more questions on the exam and harder questions. Because you're not the one taking the exam. All right. Instruction level parallelism. Oh, that's yeah. And then I see there's a request for pipelining. So instruction level parallelism is really a very fun topic. So let's all right. So it's in chapter 4. More questions means more grading. Well, we can make all questions multiple choice. And that would be a lot easier for their TAs and mentors to grade. Because it's, basically like, 5 seconds per question. No thinking, no decoding the handwriting. So I'm actually contemplating just going with multiple choice questions. For pretty much the, either the majority of questions on the test or for the entire test, because I don't think otherwise we would be able to grade it in time. Okay, so multiple choice, I generally dislike it, but for the last test, I'm seriously thinking about going with multiple choice. Well, I don't know how students feel about multiple choice. Yeah, it's easier, but then it's kind of all or nothing, right? There's no partial credit, so I don't know. It's too late for a submittee, Paul, because I have to write my questions tonight. Oh, and I see their opinions are different. Some people seem to like it. Some people clearly don't like it. All right. Yeah. Well, I'll make up my mind, but probably my major thought is making it easier on our TAs because otherwise they're just not going to be able to grade it in time. We have to get all grades Wednesday 9 a.m. All grades have to be on SIS, and if we want you folks, students, to have at least like a few hours to file a few last grade inquiries, we have to pretty much finish grading on Monday. Okay. So, and given that we still have TAs, they are the people who grade, right? I don't do grading unless there's some kind of emergency. But TAs have to grade all your projects, and those projects have write-ups. So I'm kind of leaning towards multiple choice is pretty much unavoidable. All right. Think about the students, we get paid for this. True. All right. And then.
Sorry, I'm just speaking and
Yeah.
just getting into.
Sure.
So I'm just saying, I understand, like you mentioned about zero or full credit in MCQs, but we can still have, like, as I was suggesting, a problem kind of a thing where you have 4 options. So one of them is correct. So in that manner, when your students are like just working out, they can choose one, and we can have like some partial credit also over there. So in that manner, it's still MCQ that they are choosing, but technically we are giving them that your answer should match one of these. So it might be like win-win situation for both. Just throwing that out.
Okay, yeah, we can do that. The difficulty, of course, is right. Is trying to predict which options to to give, right? Because typically when I write multiple choice questions, I would, out of let's say four options, I will do like two are, throwaway options that any, student who attended at least, some lectures should know that no, those are those two options are garbage. So they are really selecting between two options that might be somewhat close to each other. So we can totally give partial credit for one of those two real options that or how whatever the numbers might be, right? So one of three or one of two that are at least somewhat reasonable. So yeah, I hear you. We can we can try we can try doing this. Of course, the problem is, when I'm thinking about, oh, those two options are garbage, and then I see half of the class selecting one of those two options, so I could be wrong. So I think it's garbage, and it's clear to everyone that those are, throwaway options, and no one would ever consider them. But students might think differently, and that's the problem. But yeah, and I'm actually thinking about um, making more questions, but making questions shorter. So something like 10 questions each worth 10 points. Again, just to avoid cases that when someone gets a question wrong, and especially if it's multiple choice and the question is worth 25 points, that's going to be brutal. I mean, it's not going to be a disaster because we have this late drop their lower test anyways. But well, 50 questions, each worth 2 points. I don't know. People will be complaining that they don't have enough time just to read those questions, let alone answer them. And I don't have time. I don't think I would be able to produce 50 questions of any half decent quality in the time remaining before the test. I have some drafts, but still not 50, not 50 questions. All right. So yeah, let's go back to ILP and instruction level parallelism. In from the practical perspective, if I were you, I would concentrate on their multiple issue topic, right? Particularly static multiple issue, because that actually is a very nice, it's a very nice topic that I can easily come up with, with a question. So yeah, and Niho is trying to cover the TA's end of things, saying that they will be lenient. Yeah, I support my TAs in this, right? So I know it's a hard class, and I know some of you, many of you, might not agree with me, but now I was trying to make it not stressful in the end. So it's still hard material, no doubt about this. All right, but hopefully most of you should be satisfied with the grades. Okay, so we kind of tortured you throughout the semester, but hopefully we eased up towards the end, just to reduce the overall stress about the grades that, of course, all students, most students, are stressed out about their grades and their GPAs. All right. And I'm just reading a comment about their test structure and more parts to each question. Okay. Yeah. So I'll think about it. Yeah. I'll try to make it reasonable. And I know Kuzmin easy. I've seen that. It's a new meme. All right. Multiple issue. Back to the topic. So dynamic multiple issue. It's not something that I would probably be that would probably be easy for me to write a meaningful example or like a quantitative question. So we might ask some qualitative or open-ended questions, something along the lines like, compare static and dynamic multiple issue, or like, what do you think are advantages or disadvantages, something like that, some soft stuff. So, but with static multiple issue, there is this, very tempting question that, that kind of sits in my head, you know, pretty much any time we talk about this, and that would be given. So it is basically along the lines of this scheduling example. So we give you a piece of code, and then we tell you, all right, so this is the same dual issue machine, dual issue processor that we reviewed in slides. Okay, so it would be exactly this. So a packet consists of two instructions. The first instruction is always an ALU branch. The second is always load store. And we give you a piece of code. Please pack it as tightly as you can into obviously as few packets as possible. And you can do loop unrolling if you think it's advantageous. You can do register renaming. So if that helps you avoid dependencies, sure, you can do that. But you can move instructions around, so you can rearrange the order of instructions, obviously provided that the semantics of the program has not changed. Okay, and so that's a pretty typical question. I think it's it's kind of likely to appear in one form or the other on the exam. And so basically there is no like strict algorithm how you do it. You just look at the dependencies and you play with them. So I like to draw arrows, as you have seen. So it would be something like, oops, it would be something like this. All right, so here is the dependency. Okay, and what else do we have? So we have a dependency here, right? We are writing into S1 and we are reading S1 here. So that's another dependency. And so then I would just kind of, move my instructions around and see, so obviously to avoid the stall or to be, able to pack two instructions into the same packet, I need to have no dependencies. But even with this packing, right? So imagine you packed two instructions. One is like add, another is load W. But then you might have another instruction down below that still has a dependency. So an example would be, well, a counterexample would be, see how this add I writes to S1 and this BNE obviously reads from S1. So there is one packet that separates these two instructions, so there is no dependency. Whereas if we have, we might have a load use dependency, which prevent these two instructions from being in their adjacent packages. So you might need to rearrange. And so, like I said, there is. I don't think there is any kind of formal definite algorithm. So you just play. You just move around the instructions, trying to trying to make sure that you pack them as tightly as you can, and you have a minimum number of stalls, or ideally no stalls, and the minimum number of packets. Okay, so when I'm solving those problems, I literally cut. So I would have a list of instructions printed, and I would cut each instruction so I would print them on a physical paper, and I would or write them on a physical paper, and then I would just cut each instruction on its own little piece of paper, and then I would just shuffle those instructions, seeing what would be the most beneficial thing to do. So obviously you can write an official algorithm, but for the code that is sufficiently small, it might be as well faster to do, but just trial and error approach, and using your intuition than than coming up with a full correct implementation of a formal algorithm. So that's for the instruction level parallelism. So the basic idea, we should have definitely no dependencies between two instructions in the same packet. And then next, we should try to have no dependencies between instructions in adjacent packets if those dependencies would cause a stall. Okay. And the two techniques, rearranging instructions, unrolling loops like that, and renaming registers. So all those things are mentioned here in our slides. All right. So register renaming, it's right here. All right. So that's I think the the specific question that would require that you actually compute something. All right. So, and the question, of course, could be like, what would be like here? What would be the IPC, the best IPC you can get if you need to schedule this program for a dual issue processor? Okay, and then if we tell you, oh well, we can say do not use loop unrolling, or we can say then part B, use loop unrolling, and see what you get. So something, some variations of this example. I think that's highly that's highly likely. All other questions in this topic, I think, would be just conceptual, or kind of true and false, or like open-ended, explain something, or why do you think this and that. "50 questions, no. True, false." uh, all right, there was one other request to review something else. Let me scroll up to see if I can find that request. Okay, can you give a brief overview of the stuff that's going to be on pipelining on the exam? Sure. So, unlike ILP, pipelining was, an overall bigger topic. So here, there's, a bunch of stuff that we can ask about. But like I said, don't be, don't be intimidated by this topic. If you understand like how data path works, I think that's the most important thing. So things to look for in or to review as you are preparing for the exam tomorrow is, well, first is this is their pipeline, right? So the stages. So, and I don't think we're going to have any specific architecture other than the one that we reviewed. So it would be all your familiar 5 stages, and then which hardware is used at each stage, like here. And then, of course, we need to take into account those pipeline registers, the registers that separate the stages, and then Of course, so this is just a fancy way of showing a multi-cycle diagram. This is a slightly less fancy way, and the least fancy would be something along the lines of your homework, right? Where you just need to, use letters IF, ID, EX, DM, WB to show us how the execution of some program will unfold over the course of several clock cycles, and it's a it's a very high probability question, really, because it by itself tests your understanding of many topics within the pipelining. But hopefully, if you've done the homework, then you should have a pretty good understanding of what this happens. Just pay attention to what we say in the problem. Do we say that there is no forwarding? Do we say there is forwarding? Do we say that branch decision is made by their so do we have additional hardware that allows us to decide the outcome of the branch at the ID stage, or we rely on the for this, right? So typically because branch instructions need to compare two values from their registers, that would be done in an ALU. Okay, and ALU is EX stage. But in certain cases, and we have a diagram for that somewheres, and I'm trying to find it quickly. We can throw in additional hardware so that we can determine the outcome of their branching at their ID stage, and that requires an additional comparator. And yeah, so it appears right here. So you see this additional comparator that allows us to compare the values from the registers, and compare meaning basically just to subtract, right? And produce a binary flag, whether the subtraction yields 0 or not. So at the ID stage as shown here. So pay attention to what the problem says, right? Or if a diagram is given, what the diagram shows. Do we have this additional comparator here or not? If it's not here, there's no way we can determine whether the branch is taken or not at the ID stage. And 3 years in the future, Compark will require you to learn Verilog. Huh? You did you look in inside my head? I'm actually thinking about introducing Verilog in this class instead of doing all the simulations in C like we did this time. I think C is still awkward to do those hardware simulations because we have to kind of give you those artificial limitations. Do not use if, do not use for, without really giving a good explanation why, and that just that just stems from the fact that C is not meant for hardware simulations. That's it. Period. So there is the language designed specifically for that purpose. VHDL, Verilog. So yeah, and it helps you understand circuits a lot better. C is meant for ops as well. You all be taking ops if you're comp sci major. So yeah, you're gonna enjoy it. It's a lot of work. Ops is a lot of work, but I think it's an enjoyable class. All right, and so what other things we can do? So as I mentioned before, I like giving diagrams and asking questions about diagrams. So for example, we give you something like that, and we ask you to label certain inputs and outputs. Okay, so like imagine there is no 28 here, and we ask you to label this adder. Okay, so you need to figure out where this 28 is coming from, and if you do, you'd be able to label those inputs that we ask you, right? So in this case, 28 is just 7 multiplied by 4, right? And this 7 is coming from this instruction BQ, which is currently, as you see, is in their ID stage. Okay, so this is a single cycle diagram because it shows a snapshot of the processor at a given cycle. And of course, the different parts of the processor are occupied by different instructions because each of those instructions is on a certain stage of the execution. So you need to understand, how this thing happens. Like on the next clock cycle, where would our instructions be? So before 2 will leave the pipeline. Before 1 would be, so basically all those instructions would move one step to the right, as this example, as this next thing shows. So that's a very a very easy to formulate question. And of course, I love questions where I erase certain things or I break certain things, and I ask you to find out what is wrong. Like, imagine I make few changes in the diagram, and I ask you to find, to find that change. And of course, that change would be, somewhat harmful. It would break something. So, and I will ask you to find what exactly gets broken. Or an alternative of this would be, we give you a circuit, we describe what is wrong, and we ask you to identify which component is responsible or exactly what gets broken. No, G, don't be afraid. I'm not going to throw you under the bus. So no one will ever know that it was your idea because it was actually mine. I've been thinking for, especially around homework 7 and project. Which I realized that no, I don't want to do C for hardware simulations. Really, I don't think it's working very good. All right, so that's pipelining, and then data hazards and all that business. So here, make sure that you know the formulas. So if we ask you, like, write a condition to detect memory hazards. So just remember where all those formulas are coming from. Because we might not ask you just to write the formula as is, because like if you have a slide, then you would just copy the formula. That would be kind of no effort on your side. But we might ask something related to those formulas, right? But something that you have to derive knowledge, not just copy from the slide, right? And all those explanations that we went through in very fine detail, and wasted a lot of time, so that we didn't even leave enough time to for virtual memory. But like I said, I'm not particularly worried because virtual memory you will not escape virtual memory if you are taking OPSIS. So the goal of virtual memory coverage in this course is really to give you the first introduction into virtual memory, right? So remember double hazards, right? So that's also something that we talked about. Double data hazard, right? So it's right here. And that has that affects how we derive our formulas, right? Because we want to make sure that we do not, if there are multiple dependencies, like two dependencies here, that we forward from their, from this one, from their from the closest one, not from the one before. We're serious about making Windows 12 a project? Nah. All right, but someone, wrote Linux many years ago, and it was back in the times when other operating systems were existing for several decades already, and people were like, Probably. I'm just imagining, but people were like, "Oh, Linus, are you crazy? Why would you want to write yet another operating system?" Right? We have CPM, we have Unix, we have FreeBSD. Well, we have not FreeBSD. We have System 4. We have BSD. Like, why would you? Why do you think you can do better than all those professionals, who created those monstrous operating systems? And yet, see what happened, right? So Linux is everywhere. Yes, it's Unix, but you know, Unixes were around, several decades before Linux. So Linux is not exactly the same as Unix. All right. Yeah, he didn't want to pay Unix. That's true. All right. All right. We are at 9:56. So unless you want to torture me a little more, I suggest that we call it a day. I have two groups of people who wanted to talk to me after this Webex. So I'm kind of going a little into office hours mode, but just for those one person and another group of people who requested to talk to me. But hopefully that won't take long, and I will start writing your exam for tomorrow. So hopefully this was useful. Hopefully I answered some of the questions, and you feel a little better about their exam tomorrow. Yeah, it's going to be a long day tomorrow. That's true. But at the end of the day, when we are done with exams, we're going to have a little party with our TAs. So I'm that's the bright spot in my in my tomorrow. So yeah, thank you folks for stopping by, and best of luck to you tomorrow. Remember, you still have the review session with your TAs and mentors, so you can ask them any additional questions. Please review their solutions that were posted, and yeah, if anything is unclear, ask them or ask on Submiti Forum. I'm probably not going to be very responsive throughout the day tomorrow. Too much stuff planned, but hopefully TAs and mentors will take care of Submiti Forum. See you guys in PSoft. Yeah, and if you're taking PSoft next semester, then you will have me for PSoft as well. So I will see you too. I'm looking forward. All right. Thank you, folks. And so we have then two groups that I wanted to talk to, or that wanted to talk to me. So let me stop the recording now.